Hello, everybody. We are going to start talking about something new today. We're going to talk about polar coordinates. And just a few things. Remember when we were graphing equations in algebra, we used the rectangular coordinate system, the XY plane. Let me see if I can get this to focus a little bit better. That's a little bit better. Okay, the XY plane. When we think about plotting points or graphing on the XY plane, we have the origin at the center, which is the point where x is 0, y is 0. And when we think about any point, for example, if we want to look at the point -2, +1, this is saying we have an x value of -2, we have a y value of +1. So from the origin, we go to the left, -2, and we go up, +1, and right there's that point. Those are called rectangular coordinates. It's the way we've graphed a lot before. It's what we're used to. We could be on an axis itself. If we wanted to graph the point 0, -3, x is 0, so we're still at center. X deals with left and right. Y deals with up and down. 0, -1, -2, -3 would be a point on the y-axis. So lots of different ways that we can graph. Well, we have another type of system we can use for graphing. They're called polar coordinates. And when we think about polar coordinates, these are used to refer to the same points, really, as your x and y points, but we use distance and direction to help us identify where the points are instead of an x and a y value to depend on where the guys are. So let's look, for example, at something we've done in the past. Okay. From the unit circle, we know we have a circle centered at 0, 0 with a radius of 1. So if we think about this, rough sketch, I am not an artist, I am sorry. But we think about our x-axis here and our y-axis here. The unit circle is centered at the point 0, 0. And for a unit circle, the radius is equal to 1. So for example, let's consider the angle pi over 6. Pi over 6 would be this angle right here. Okay, we have a radius of 1. And what do we know from the unit circle? We know that the point that lies on the unit circle has an x value of the square root of 3 over 2 and a y value of 1/2. This point is a rectangular coordinates. Okay, it's in the form x and y. Our x value is here. Our y value is here. There's the 1/2 for the y. Here's the root 3 over 2, which is the x. So those are our rectangular coordinates. As we look at this, we can also think of these things as distance and direction. And here's the idea with polar coordinate system. We have some fixed point, O, okay? We stretch a ray out from O. So this O is called the pole or the origin. Okay. This axis out to the right is called the polar axis. And then we use an angle we have some radius r, which is this length of this ray, to get to this point P, okay? And so what we can talk about with this point in polar coordinate form is we use the r value, the radius, and the angle value gives us the direction. So the angle is telling us the direction we're going, the radius is telling us how far out from center we are, and that helps us locate that point. So when we look at this, here's something to remember as you go through, okay? Remember with angles, when we went counterclockwise, they were positive. When we went clockwise, they were negative. So we'll remember that as we go through. In our last example, the rectangular coordinate of √3/2 and 1/2, if we think of the pole as being the center of that circle, that origin, O, our radius is 1, our angle is a positive pi/6. So our polar coordinate will be the ordered pair, or it's not an ordered pair, but it will be the coordinates where we have our R value of 1 and our angle value of pi/6. These are pinpointing the exact same point, okay? It's just telling us how we're getting there. So they're equivalent, just written in a different form. Now, in the same way that we thought about angles being positive up to the left, negative if we went clockwise down to the right, what we're going to do as we think about plotting things in polar coordinate form is usually with our radius, we think of a positive value, okay? If we have a negative R, we have a different way that we'll deal with it, and I'll show you that in just a minute. But let's look at some plots for polar coordinates. Now, notice what I've done. This right here is my x-axis. This right here is my y-axis, okay? And then what I've done is I've made circles radiating out from the center. So we have our origin or our pole, 0, okay? We have our polar axis going to the right, and we want to plot this point where we have the polar coordinates 3 and 4 pi/3. 3 is your radius, 4 pi/3 is your deals with your direction. So think about what that direction of 4 pi/3 would look like on this graph. We've done this before. 4 pi/3, if we start in the standard position, here's pi/3, 2 pi/3, 3 pi/3, 4 pi/3 is down here, okay? 4 pi/3 gets us down to a terminating ray down here. The point on the graph, the radius, the distance is 3 from the center. If it is a positive R, okay, then it's going to lie on the terminating side. And think of each circle being a unit out. So here's 1 unit out, 2 units out, 3 units out on the terminating or the angle 4 pi/3. This is our point. This point right here is 4 pi/3, okay? That's the location. If you have a positive R value, it's going to be on the terminating side of wherever that angle lands, okay? Let's just look at a couple more examples here. Let's look at this one. 2 negative pi/4. Now our direction deals with the angle, negative pi/4. Now what I have here, this represents negative pi/6. This represents negative pi/3. This one I didn't actually have a negative pi/4 in there. It'd be about halfway between the polar axis and the terminating side going downward. So right there is our terminating side for negative pi/4. Now our R value is a 2. It's positive. So we're going to go 2 units out on the terminating side of this angle. So 1 unit, 2 units out would be right here. Okay? That point is our point to negative pi over 4. That's how we plot polar coordinates. Let's look at this guy. Now here we have a negative. Now direction is 5 pi over 6. Think about where 5 pi over 6 lies. So here's pi over 6, 2 pi over 6, 3 pi over 6, 4, 5. Right here is our 5 pi over 6, terminating side for the angle 5 pi over 6. Here's what you do when you have a negative r. This r equals negative 4 means you're 4 units out, but that negative means in the opposite direction. So instead of lying on the terminating side, 4 units out on the terminating side would be right here. Go the opposite direction. I'll dash in the opposite direction here. So we're going to go 4 units out in the opposite direction. 1, 2, 3, 4. Right there is that point, negative 4, 5 pi over 6. Now we know with circles, they go round and round and round. You have all kinds of coterminal angles, right? We could think of this a lot of ways. This point, negative 4 and 5 pi over 6. Think about another way we could write this. What if I want that to be a positive 4 instead of a negative 4? That means my terminating side would have needed to be right here. Okay? So think about that. I could write that terminating side as a negative pi over 6, or I could write that terminating side as an 11 pi over 6. There are infinitely many ways to write these polar coordinates because there are infinitely many ways to write an angle. We have all kinds of coterminal angles. But if you're wanting to plot a polar coordinate, this is what you do. You use the angle to tell you which direction and where the terminating side is going to be. If it's a positive radius, the point lies on the terminating side. If it's a negative radius, the point lies on the opposite of the terminating side. Okay? Let's look at one more here. Negative 5 and 3 pi. Well, again, if we look at this, we have 3 pi, so that's my direction. Think about where 3 pi would lie. 0's here, pi is here, 2 pi is here. If I kept going around 2 pi, if I go around another half circle, that's 3 pi, 4 pi, 5 pi, 6 pi. Any whole number multiple of pi is going to be somewhere on this x-axis. Odd multiples of pi to the left, positive multiples of pi to the right. So our terminating side for 3 pi is right here. Okay? Right there's our terminating side for 3 pi. Our radius is negative 5. So that means we go in the opposite direction 5 units. So instead of being out here, 1, 2, 3, 4, 5, we're going to go the other direction. 1, 2, 3, 4, 5. Right here is the point negative 5 and 3 pi. Okay? So there are a few problems in the notes that you can practice and just kind of get familiar with as we go through. But the big key thing to remember as we look at any of these guys is rectangular coordinates are going to be what you're used to, those x, y ordered pairs, okay? The polar coordinates are always going to be in the form radius and direction, angle, okay? Infinitely many ways we can write this. One right here. Only one way we can write the x, y. but keep those in mind. We're going to talk a lot in this section about converting between the two. So let's start with that. We want to convert between rectangular coordinates and polar coordinates. Now, when we first defined trig functions, we knew that for any angle, the cosine of theta is equal to x over r, and the sine of theta is equal to whatever the y-coordinate is over r. We could actually solve each of these. So for example, if cosine of theta is equal to x over r, I could multiply both sides by r, and I get x is equal to r times the cosine of theta. Okay. We also know that we know that sine theta is equal to y over r. So if we multiply both sides by r, the r's cancel over here. Y is equal to r times the sine of theta. We can use these to go between two different types of things here. Okay, just a second. Okay, sorry about that. I've told you all before, well, I've mentioned it in past videos. There's a 60-pound boxer here. She got into something. I just needed to stop for a second. All right, let's look at this example. Now, we got to the point where we knew x was equal to r times cosine theta and y is equal to r times the sine of theta. This will always be true. Okay, this will always be true. Just a second. Come on. So make sure you know these guys. Okay, we're going to use them a lot. They're definitely relationships you want to know, just like the relationship where they came from, that cosine is x over r and sine is y over r. So we want to make sure that we're familiar with those as we go. Now, we can use these to help us convert. If we're given a polar coordinates and we want to convert to rectangular coordinates, remember, polar coordinates are in the form r theta. Rectangular coordinates are in the form x and y. So we're given, for example, this point right here. So we know that r is equal to 4 and theta is equal to pi over 6. Well, notice by knowing these relationships, x is equal to r cosine theta, y is equal to r sine theta, when we're trying to get the rectangular form, which is an xy ordered pair, this is going to be a pretty quick substitute and evaluate. Our x value we know is r times the cosine of theta. Our r value is 4. Cosine of theta is pi over 6. Well, the cosine of pi over 6 is square root of 3 over 2. So we have 4 times square root of 3 over 2, which is 2 square root of 3. So we know that our x value is 2, whoops, I didn't need a comma there, did I? Is a 2 square root of 3, okay? Now our y value is always going to be r times the sine of theta. Our r value is 4 times the sine of theta, which is pi over 6. Sine of pi over 6 is 1/2, and 4 times 1/2 is 2. So our y value is 2. This point as a polar coordinate is equivalent to this point as a rectangular coordinate. This is when the pole, which we called 0, is at the origin 0, 0 of the XY coordinate system. As long as that's true, this is what we have going on, and we can convert between the two. It's usually a pretty quick conversion when you start with a polar coordinate and you're going to rectangular form, because it's a direct application of those formulas, okay? Know these. We're going to use them a lot. Okay. Let's look at another example here. Whoops. Convert square root of 2 negative pi over 4 to rectangular coordinates. So we're converting to rectangular form. That means we want the XY ordered pair. What is that? Remember that x is equal to r times the cosine of theta. So that means x is equal to the square root of 2 in our polar coordinates. This is our r value. This is our theta. Oops, sorry. So we have the square root of 2 times the cosine of negative pi over 4. The cosine of negative pi over 4, that's in quadrant 4. And cosine is positive in quadrant 4. That's a root 2 over 2 times square root of 2. So this ends up giving us 2 over 2, which is 1. So for this one, we have an x value of 1. We know that y is equal to r times the sine of theta. So that means y would be square root of 2 times the sine of negative pi over 4. Again, negative pi over 4 is in quadrant 4. So sine is going to be negative. And at any of the over 4 angles, it's a root 2 over 2. So that's negative square root of 2 over 2 times square root of 2. This is going to be a negative 2 over 2, or negative 1. So the coordinates 1, negative 1 are the rectangular coordinate form of the polar coordinates square root of 2, negative pi over 4. They're equivalent, okay? So we can look at them a lot of different ways. So try a couple, see how you do with those. But those are going to be direct applications of those two identities, which we know. X is always r times cosine theta. Y is always r times sine theta. We can use that throughout. Know it, know it, know it. Okay? All right. We can also go backwards. We can go from rectangular coordinates to polar coordinates. Now, when we think about this, rectangular coordinates are plotted on the rectangular coordinate system centered at 0, 0. There are a couple of other things that we're going to find really useful that can help us out when we convert back and forth between rectangular and polar, okay? The equivalent polar coordinates, so if we have the rectangular coordinates, we know we have the XY coordinate system centered at 0, 0. Polar coordinates, when we looked at those graphs earlier, I set the pole of 0 at the center, and then we looked at the circles radiating out from that, right? Where it depended on our radius. But we have circles centered at 0, 0. So we really have, with polar, we have a pole, we have circles centered at 0, 0. The general equation of a circle is x minus h squared plus y minus k squared equals r squared, where the center is 0, 0, h is 0, k is 0. So this would be x squared plus y squared equals r squared. For all of these polar coordinates that are equivalent to rectangular coordinates, this is going to be true because it's going to fit a circle centered at 0, 0. Know that because we are going to use that as we go. We also know something else. If we're interested in an angle, think about things that we know when we were dealing with circles before. a lot of stuff that we've used in the past here. If we have a circle centered at 0, 0, again, I am sorry for this sketch. I am not an artist, okay? So if we have any terminating side, I'll just look at one here, okay? So here we have our angle theta. Notice we can imagine a right triangle here where we have our x value and our y value. So we could actually get this because tangent of theta is opposite over adjacent, or it's y over x. Tangent of theta is y over x as long as x is not 0, which means that theta is equal to the inverse tangent of y over x as long as x is not 0, okay? These are two concepts, whichever form you think about those in. Tangent of theta is always y over x. Back when we learned cosine of theta was x over r, sine of theta was y over r, tangent of theta was y over x. And that's always going to be true. So we can use these facts as well to help us find different values. Okay, let's look at a couple of examples. What I want to do now is I'm wanting to convert from knowing x and y to needing r and theta. Okay, so let's look at this one. For each of the following, convert the rectangular coordinates xi, xy to polar coordinates r, theta, where r is positive and theta is somewhere in the first revolution of the unit circle. We saw that we could have infinitely many, okay? We could have infinitely many ways to write a polar coordinate because we have infinite coterminal angles. We'll go ahead and do it so that we have an angle just within one revolution and we're on the terminating side, so our R value is positive. So look at this first example. We are given an x value of root 8 and a y value of square root of 8. We need the polar coordinates, which will be in the form r and theta. So we need r and theta. Well, we know from what we just looked at that x squared plus y squared is always going to be equal to r squared. Because we have our circle centered at the origin 0, 0, this is always going to be true. We know what x is. So that's square root of 8 squared. We know what y is. That's square root of 8 squared. That's going to be equal to r squared. So this is 8 plus 8 equals r squared. 16 is equal to r squared. So r would be equal to plus or minus the square root of 16, which is plus or minus 4. Now, since we're wanting it to be on the terminating side of theta, we're going to go with the positive version only. So our r value is 4. That's our radius. Okay. We also need theta. Well, the other thing that we just looked at was we know that tangent of theta is always y over x. So that means tangent of theta would be equal to our y value is square root of 8. Our x value is square root of 8. So tangent of theta is equal to 1, which means that theta is equal to the inverse tangent of 1. Okay. And the inverse tangent of 1 is pi over 4. So we know theta is pi over 4. These are the polar coordinates that go along with those rectangular coordinates, root 8, root 8. Okay? Right? So again, the two things that we looked at just a minute ago are really useful. We know the equation's always going to fit x squared plus y squared equals r squared. And we always know that the tangent of an angle is y over x. Since a rectangular coordinate, you're always given x and y, you'll always be able to find r and you'll always be able to find theta. Okay? Now, here's the thing. This was a nice number. We knew that the inverse tangent of 1 was pi over 4. That was an exact value. Sometimes it won't come out to be an exact value. So if you're asked to give exact, you might have to write it as an inverse tangent. Let's look at this next guy. So we have an x value of -3, and we have a y value of 4. We want the polar coordinates, so the r theta form. Well, again, we know x squared plus y squared equals r squared. X is -3, so we have -3 squared plus y is 4. 4 squared equals r squared. So that's 9 plus 16 equals r squared. 25 equals r squared. So r is plus or minus root 25, which is plus or minus 5. Now again, our directions said we wanted the positive version. So we know it's radiating out at a radius of 5. Okay. Let's go ahead and look. All right. So we want just the positive 5 for our r value. Now, we also know that the tangent of theta is equal to y over x. So tangent of theta is equal to 4 over -3, which is -4/3. So theta would be equal to the inverse tangent of -4/3. Now here's the thing. There is not a nice angle on our unit circle that will give us a tangent of -4/3. Think about what our tangent values look like on the unit circle. We had 1 if it was a pi over 4 angle. We had square root of 3 involved if it was a pi over 3 angle. Okay. We had root 3 over 3 involved if it was a pi over 6 angle. So we had different things involved there. And let me think. Yeah. Nope. 2 root 3 over 3, sorry, if it was a pi over 6 angle. But we didn't have any 4/3. Therefore, we don't have an exact value here. So if we want an exact value, we're going to have to write it as inverse tangent of -4/3, okay? And that is the polar coordinate form. This would be an exact answer. So if you wanted an exact answer, that's what we're going to have for this one, okay? If you want an approximate answer, if it says round 3 decimal places, okay, then we'll have 5. Go ahead and grab your calculator and do inverse tangent of -4/3, and you'll get a -0.927 if you round 3 decimal places. So if it asks you to round it. Okay. But here's the thing too. Usually what do? The problem said to write your angle. The directions initially before all this said we wanted our angle to be something between 0 and 2 pi. This is a negative. So let me go up by 2 pi. This would actually be 5. And if you went up by, wait a second. Sorry, I got distracted here for a second. Okay, when we look at this, remember, inverse tangent is always going to give you a value between -pi/2 and pi/2, okay? What quadrant are we in? -3, 4 is in quadrant 2, okay? So what we need is to figure out what this theta is in quadrant 2. This is in quadrant 4, okay? So basically what's happening is this. You're getting the negative 0.927 down here. Remember reference angles. If we're in quadrant 2, this is our reference angle. To get our theta for quadrant 2, our reference angle is, we are going to take pi and reduce it by 0.927. So theta is going to be pi minus 0.927. Okay. And pi minus 0.927 is 2.213. Okay, as we look through. So if we go through, that's going to be our approximate value there. We do need to convert it, remember which quadrant we're in, and use our reference angle to get there. Okay, all right. Let's go ahead and keep going. Look at this one. We want to convert, again, a rectangular coordinate. So x is 0, y is square root of 3, to polar coordinates. Polar coordinates are in the form r and then theta. Go ahead and pause, take a minute to do this, then check yourself. We know that x squared plus y squared equals r squared. That's 0 squared plus square root of 3 squared equals r squared. That's 0 plus 3. Sorry. Go. Okay. So we have 0 squared plus square root of 3 squared equals r squared. That's 0 plus 3 equals r squared. And remember, we're wanting to just deal with the positive r value, so that's square root of 3. So we know our r value is square root of 3. That's the distance from the pole. We also know that tangent of theta is equal to y over x. So tangent of theta is the square root of 3 over, 0. That's going to be a problem, huh? X can't be 0. To use that guy, okay? But think about what's going on. Think about that 0.03. So if you have a rectangular coordinate, so there's our y-axis, there's our x-axis, okay? If we have the point 0 root 3, the x value is 0, the y value is 3. Notice we just said radius is root 3. That made sense. From the pole to the point, square distance is square root of 3. What's your angle? Theta. If you have a 0 for x and a positive y value, you're at the angle pi over 2. So we didn't have to use the idea of tangent with these. If your x value is 0, if you have a positive y value, your theta is going to be pi over 2. If you have a negative y value, your theta is 3 pi over 2. You're on the y-axis, okay? So that one was a little bit different. We had to know where the point was to go for it. So try converting between rectangular coordinates and polar coordinates. Remember all of the things that we've used, and you want to make sure you know them. We know that x is equal to r times cosine theta every time. Y is equal to r times sine theta. We know x squared plus y squared equals r squared. We know that tangent of theta is always going to be y over x, as long as x is not 0. We just saw a case where x was 0, but that made it easier because we actually knew where on the coordinate system it was and what the angle was. So that wasn't too bad. Make sure you know all these. The more you know them, the faster working with them will be. Now, equations. Remember, when you think equations, think of an equal to, okay? When we're talking about rectangular equations, we're going to have equations that have x's and y's involved, no r's and thetas. When we have polar equations, we're going to have r's and thetas involved, no x's and y's. So we want to start and be able to convert between rectangular and polar equations in either order. These are our useful guys that we're going to make a lot of use of in this section, okay? So let's go through and look at some examples. Look at this first one, number 17. Convert the polar equation to an equation in rectangular form. Polar equation means it has r's and thetas involved. Rectangular form means we have x's and y's involved in the equation. We're given r times cosine theta equals 6. This one is actually going to be a pretty quick one because remember, we know that x is always equal to r times the cosine of theta. That was one of the things that we just used that we know is always true. We have an r times cosine theta here, so we know that this is x. So we have x equals 6. We have an equation. It has no r's and thetas. It only has x. It only has an x. You don't have to have a y. X equals 6 is a vertical line. Okay. When we look at the XY coordinate system and we look at a graph, that's a vertical line. X equals 6. That is a rectangular form of an equation. So that one was really quick. Let's look at number 18. We have r equals 4 times the sine of theta. Now, we know that y is equal to r times the sine of theta. So if we had an r sine theta, we'd be golden for the y. Notice I don't have an r here, okay? But I could get an r. We could multiply both sides of this by r. And what we would get would be r squared equals 4 times sine theta times r would be the same as 4 times r times sine theta, okay? So when we look at this, we automatically see that the r times sine theta is a y. So over here, we have a 4 times y. Now look over here on the left. We have an r squared. Do we know anything about r squared? Think about the things that we had before, okay? Remember, we know that x squared plus y squared is equal to r squared. So we have an r squared. We can replace with x squared plus y squared. So I have x squared plus y squared equals 4y. Okay. Notice at this point, we only have x's and y's, no r's and thetas. So good. We now have something that's rectangular in form. Okay. We now have something rectangular in form. Now I'm going to take this a little bit further. When you check, so especially with our current text, when you check your answers of this, because so many of our equations, when we have x squareds and y squareds involved, so many of these fit circles. And so if you have an x squared and a y squared involved, then what we're going to do is we're going to go ahead and put this in the general equation of a circle. So I am going to do a little bit of a conversion here, okay? We know that circles fit the form x minus h squared plus y minus k squared equals radius squared, all right? So if we want to take this equation and get it in this form, we're going to have to use a process called completing the square. And I know it's been a little while since a few people have done completing the square. But the first thing we're going to want to do is get the variables on the left, constants on the right. Well, I have a positive 4y here, so I'm going to subtract 4y from both sides. And I have x squared plus y squared minus 4y equals 0. So I have this form, variables on the left, constants on the right. Now, the only place I see an x is right here. So I have x squared. Notice that's the same as x minus 0 squared. So what that means is our circle is going to have a center of an x value of 0, okay? I'm just going to leave that as x squared in the equation, but that's the x value of the circle. But this part right here, y squared minus 4y, we want to write that as a binomial squared, okay? So in order to do that, the completing the square process, you take half, well, first of all, you need a 1 as the coefficient of your y squared, and we have a 1 as coefficient of y squared. Take half of your coefficient of y. So half of negative 4 is negative 2. Square it. Negative 2 squared is 4. This is what we're going to add to both sides of this equation. So I'm going to go plus 4 plus 4. So over here on the right, I have a 4, because whatever you do to one side, you have to do to the other. And what happens is this part right here, y squared minus 4y plus 4, actually factors to be y minus 2 quantity squared. So here's the general equation of our circle, where our x value is 0. At the center, our y value is 2. And this is radius squared, so the radius must be 2. So we have a circle that is centered at 0, 2 with a radius of 2. But this is our equation in polar form, okay? So we can go through and write it a little bit differently. We can do the conversion and write it in the form of a circle if you have x squared and y squared involved, okay? All right, that was example 18. Let's try another one here. Example 19. Convert to rectangular form. So again, we have it in polar form. We have r equals negative 5. Rectangular form is going to involve x's and y's. We know that x squared plus y squared is equal to r squared. We know that the tangent of theta is equal to y over x. We have a few things involved here that can help us with r's and thetas. Well, we just have an r right now, okay? There are actually a couple of ways that we can approach this. R squared is equal to x squared plus y squared, so that means that r would be the square root. You could think of it like that, or you could think of squaring both sides of this equation. This would give us r squared equals 25, and we know r squared is x squared plus y squared. So we have x squared plus y squared equals 25, okay? We have x's, we have y's. We actually already have this in the form. This is a circle with a center of 0, 0 and a radius of 5. And that makes sense for r equals negative 5. Think about what r equals negative 5 would look like. Any point, any direction you went out, if you went out 5 units in any direction from the center, you'd have a radius of negative 5 because it could be the opposite side. So that's what we have there. That one didn't take too much, okay? Try a couple, see what questions you have, let me know. you're having any problems with them. We can do the opposite direction as well. Now remember everything we know. We know x is equal to r cosine theta. Y is equal to r sine theta. We know r squared is equal to x squared plus y squared. We know that tangent of theta is equal to y over x as long as x is not 0. All of those things are useful. I write them a lot because really the process of remembering things helps. The more you write it, the better you're going to remember it. So let's try converting from from rectangular to polar equations. We're going to do the opposite that we just did. We're starting with things with x's and y's, and we're wanting to get in a form where we have r's and thetas, okay? Now with this one, this is going to take a little bit more of a direct approach because we know that x is equal to r cosine theta and y is equal to r sine theta. So I know that y is r times the sine of theta, and I know that x is r times the cosine of theta squared. Okay. So I have r sine theta is equal to r squared cosine squared theta. Now, your goal when you're writing polar equations is to get it in the form r equals everything else. Okay, we want to solve for r. We want to get it in that form. Now notice, we can do a couple of things here. First of all, we can divide both sides by r. That gives us sine theta equals r cosine squared theta. We can do that. Okay. Now, back when you were solving by factoring, think about when you had algebra equations and you were factoring, and if you had something like this. If you had r squared cosine theta equals r sine theta, and when we tried solving by factoring, we got 0 on one side. So that's r squared cosine theta minus r sine theta. You could factor an r out, but that was cosine squared theta, excuse me. So either r is 0 or r cosine squared theta minus sine theta is equal to 0, and that's where this guy comes from, if I add a sine theta to both sides. When you do something like this and you have an r and you have an r squared on each side, a solution of r equals 0, you won't have a circle if the radius is 0. You won't have a circle. So that's why that option isn't actually an option for your solution. So that's why we can get by with going ahead and dividing both sides by r and getting sine theta equals r cosine squared theta. We want to solve for r, so I'm going to divide both sides by cosine squared theta. So I have r equals sine theta over cosine squared theta. Now, it's always good to simplify this if you can. And we could think of this as sine theta over cosine of theta times 1 over cosine theta. Because cosine times cosine is cosine squared. Sine times 1 is sine theta. And that's equal to tangent of theta times secant of theta. So our equation is r equals tangent of theta, secant of theta. In either order, we could have written secant times tangent. But that's our equation in polar form. R equals, and it's given in terms of theta. In rectangular equations, your variables will be x's and y's. In polar equations, your variables will be r's and thetas. Okay? So let's look at the next one. X squared is equal to 4y. Now again, x is r cosine theta. So that's r cosine theta squared. equals 4 times y is r sine theta. So we have r squared cosine squared theta equals 4r sine theta. Okay. So same idea. We have a factor of r on each side. I could divide both sides by r. And that's going to give me an r cosine squared theta equals 4 sine theta. Remember, your goal is to solve for r. So I'm going to divide both sides by cosine squared theta. So r is equal to 4 sine theta over cosine squared theta. Now we can write this as 4 times sine theta over cosine theta times 1 over cosine theta. That would be the same thing. So that would be 4 tangent of theta secant of theta. So our answer for this one is r equals 4 times the tangent of theta secant of theta. Very similar to the first one we did. But there's your idea. You want to solve and get it in the form r equals. Okay? Let's look at one more example for today, and we'll close this video up. Try some of your homework, see what questions you have. Okay? Look at this one. X equals 4. Again, what is x? X is r cosine theta. So, r cosine theta is equal to 4. We'll undo the multiplication by dividing both sides by cosine of theta. So r is equal to 4 over cosine theta. That's the same thing as 4 times the secant of theta. So I could write this as r equals 4 secant theta. That's in polar form. An equation in polar form is going to be in the form r equals, where we have our angles. Our variables are the r and the theta. Okay? So try your problems from this section, see what types of questions you have, and I will share a video that involves the try questions from the notes. Okay? Yell if you need me.